right, can everybody see that okay?
Mm-hmm. You want to enlarge it, make it big?
Yeah. There we go. All right, let me just find my, there we go. Perfect. All right, well, hello everybody, I'm Ben Stark, and today I'll be talking to you about the photovoltaics and the photovoltaic effect. The photovoltaic effect is the phenomenon that makes photovoltaics possible. So a quick rundown of what the photovoltaic effect is. Basically, you've got two semiconductors. One has an excess of electrons and one has spaces for those electrons to go. Sunlight hits these semiconductors and excites the electrons, and it creates an electric field that we can harness to generate electricity. Quick history of the photovoltaic effect. This guy here is Edmund Becquerel. In 1839, at age 19, he was credited with discovering the photovoltaic effect. This is a little example of this experiment. The experiment consisted of platinum electrodes, which you can see here. They were coated in silver bromide and suspended in an acidic solution. Exposing these electrodes to sunlight resulted in a current being generated. And then flash forward about 114 years, 1953, Bell Laboratories unveiled the first commercially practical solar cell. This was a silicone solar cell, so they moved from wet to solid cells. It had an efficiency of about 6%, which was comparable to gas engines at the time, although obviously it couldn't generate as much power. And these are the three gentlemen that are credited with developing that silicone cell. And today, solar is found all over the globe. It's the fastest growing form of renewable energy. Let's see. Looks like, okay, sorry about that. This is a solar panel, a solar park in the Middle East. And then this one here is the first floating solar park in China. And the water, not only does this use space that otherwise wouldn't be used, but the water also helps to keep the panels at a cooler temperature, making them more efficient. So this is a map that shows where most of the solar power is being generated worldwide. You can see that China, India, Germany, and the United States are the leaders, up in the range of over 80 terawatt hours. This is a little rundown of the kind of the insides of a typical solar panel. On the left here, we have a typical solar cell. So you can see we've got the two silicone semiconductors, the P-type, the positive stands for positive type, and then the N-type for negative. And then we've got electrical connections on either side to grab that those electrons that get moved around by when light hits the panels, and then it's all sealed up with glass and held together with an aluminum frame. And then this is just a layout. So we got a cell here, and then this is a layout of a whole panel. You've got the junction box, the back sheet. EVA is just a kind of a protective weatherproofing layer. Yeah. So I'll do a rundown of the three types of solar cells that are most common. Start with the monocrystalline. Monocrystalline cells, basically what that means is that each cell in the panel is made from a single silicone crystal. This is an example of what a single silicone crystal looks like. They're massive. These aren't found naturally like this, but they can be manufactured. the manufacturing process is pretty intensive compared to some of the other methods for making cells. Some of the pros of monocrystalline panels, they have a higher efficiency rating, and they have a longer lifespan. Some of the cons, they're more expensive than some of the other variations, and they are less sustainable. The production process does require more energy. Another common type of panel is the polycrystalline. Unlike monocrystalline, which is made from a single cell, polycrystalline is multiple cells. They basically take a whole bunch of pieces of silicone and heat them up and turn them into a cell, but all the little individual crystals maintain their structure as opposed to becoming a uniform structure. And you can kind of see that here on the right. They are less expensive than monocrystalline, and the production is more sustainable. It's not as energy intensive. One of the cons, though, is that it is less efficient than monocrystalline, and it does have a shorter lifespan. Monocrystalline and polycrystalline are the two types that you will see in residential use for the most part. The third type is the thin film photovoltaic panels. These are the types that you'll generally see in large solar farm operations, just because they are very cost effective, and you can make up for the lack of efficiency with a lot of land. If you've got a lot of land, then you can skimp on investing in panels and just make up for it by the number of panels that you have. These are produced by actually spraying, as opposed to heating up and making semiconductor wafers like the polycrystalline and monocrystalline. These are actually sprayed onto a glass backer. A company called First Solar is the dominant producer of thin cell photovoltaics worldwide, and they use a cadmium tellurium mixture. There are all kinds of, typically the positive and negative is provided by boron and phosphorus. That's what you see in a lot of cells, but you can make all kinds of semiconductors with different elements that will capture different wavelengths of the light spectrum. Oh, and I forgot to mention, if we go back to monocrystalline panels, they have a lifespan of generally 25 to 35 years. And the average efficiency for monocrystalline is 22 to 27%. As far as polycrystalline, they have efficiency ratings of between 15 and 22%, and they can last anywhere between 23 and 27 years on average. And thin film photovoltaics, their efficiency rating can be as low as 7% and as high as 22%, and they usually last between 10 and 15 years. I'll give you a quick rundown on PV cell production, and I'll just use monocrystalline as an example. So the first step is they extract quartz sand and put it into an arc furnace. If you want to see something wild, look these up on YouTube. It's like a fireworks display in a can. Basically, these are three electrodes that are carrying a lot of power, and they get inserted into the sand and they melt it. And this is kind of a cross section of that process. As you go farther down into this pit, the temperature gets hotter, and that heating process also purifies the silicone and gets rid of impurities, and then the pure liquid silicone is discharged. After you have that discharge, after you've purified that silicone, that goes into this furnace here. Basically, this is a kind of showing you the process here. You basically have a seed crystal and then your molten silicone. That seed crystal gets lowered into the molten silicone, and then this whole platform is lowered. And as it lowers, the seed crystal provides the basis for which the rest of the crystal kind of builds itself around. So yeah, you got your silicone melt, the crystal gets inserted, and then the entire crucible, I guess, gets lowered, and the crystal kind of gets pulled out of it like magic, and then more silicone is added to fill that crucible back up. Some examples of large-scale photovoltaic applications. Let's see. Okay, yes, this was a picture that I showed earlier. This is the MBR solar park near Dubai. This particular park spans 30 square miles and is being built in phases. When phase 5 is completed, it will be the largest single-site solar plant in the world with an estimated capacity of 5,000 megawatts. This is the Badla solar park in India, and I thought this was really cool just because you could see the progress. These are satellite photographs. 2016, not much going on, but by the time 2020 rolled around, the development was pretty extensive. It has a production capacity, a power production capacity of 2,245 megawatts and covers roughly 57 square kilometers. And this is that picture I showed earlier of the Anhui floating solar park in China. I wasn't able to track down any solid numbers on its power production, but I just thought that design concept was really innovative, and just the fact that it helps to keep the panel efficiency ratings higher because they're not operating at such high temperatures. Small photovoltaic applications, obviously homes and businesses, although you don't really see them on businesses very often. It's generally residential. Car charging stations, there are quite a few of these in Europe, not as many in the US, but hopefully that'll start to change. And you can when it comes to residential applications, you can either power your entire house off of solar, or you can use solar to power specific appliances in your home, maybe like a hot water heater, or other appliances that you want powered by solar. Whenever you have solar panels installed, you also need to install an inverter that converts the power generated from DC to AC. One thing to consider is you can either have one inverter that handles all of your panels, or each panel can have an individual inverter. I would recommend having an inverter for each panel, because if you only have one inverter, then it is anytime there's partial shade on one of your panels, the inverter basically has to drop to the lowest denominator and provide power based on I didn't quite fully understand the concept, but basically if you have an inverter on each panel, it maximizes the amount of power you can get, as opposed to just having one inverter for your entire solar system. This was another statistic I thought was interesting. This just shows the installed photovoltaics capacity per capita. And Germany, which we saw on that other map, was high up there for power production, and it's also #1 for power production per inhabitant. Yeah, they pretty much blow everybody else away. But I thought that was pretty interesting. This was something else I found. I'd highly recommend checking out the NREL website if you're looking for more information on solar. They're a really good resource, and they provide a lot of information. Basically, I wanted to show this to demonstrate the advances in how quickly we've been able to increase solar efficiency. So here we have single cell non-concentrator. That's basically the monocrystalline panel that I was talking about, or monocrystalline photocell that I was talking about earlier. That was developed around 1977. And then over here we have the perovskite cells, which were developed in 2013, and they both pretty much, so this is time, and then here we have efficiency percentages. They both start roughly around 14% when each was introduced. Let's see, and then here's kind of where they both are today, and they're both right around roughly 26% percent. You know, we got 26.1 and 25.5. But the perovskite was able to accomplish that in 7 years, as opposed to single crystal, which it took, I think, 22 years. I think I stopped here just because it kind of flatlined for a long time. But I just thought that was kind of cool. You know, the panels that are being introduced more recently are gaining efficiency at a much faster rate than some of the cells that were introduced earlier. So when you're deciding whether or not to choose to use solar on your home, there are definitely some practical considerations. One is geographic location. Obviously, you know, sunlight isn't spread equally across the United States. So you'll want to take that into consideration when choosing solar. And then if you've decided that your area gets enough sunlight to make solar worth it, you need to also determine how your home is oriented. Generally, you want at least one part of your roof to be facing south, because that's where you'll get the most sunlight exposure. And the angle is not as much of an issue because the mounting brackets can make up for the angle of your roof if it's too sloped. Not so much if it's too steep, but you can kind of work around that more easily than you can the direction of your roof. This was a chart that I found really useful. We've got the orientation of your roof and then the tilt, and it kind of shows you where the sweet spot is. You want to, you know, if you can be facing directly south and at about, let's see, 30 degrees or so, or yeah, between 30 and 40 degrees. That's kind of your ideal orientation and angle. I mean, you've got a lot of you know, you can, let's see, yeah, you can be, 15 degrees either way and still be fine. But I just thought this was a really useful chart for kind of determining what your maximum efficiency can be. This is another great NREL. This is just kind of further showing the amount of irradiance in the United States. This is the average over the course of a year. You can obviously see that the Southwest gets the most exposure, and then it kind of decreases as you move out from there. And this is measured in kilowatt hours per meter squared per day. And then I was able to go from there, and this is just that same map, but instead of showing the annual average, it shows my month by month the average sunlight. So we've got January, April, May to August, September to December. So yeah, April through September or August, you've got pretty good coverage through most of the US, and then, you know, obviously during the winter months it really drops down rapidly. Other practical considerations, the available space that you have, that'll determine what kind of panels you're going to use. I've heard that recently the efficiency differences between monocell and polycell have gotten closer together. Polycells have become more efficient and more appealing just because they have a lower cost, and they're not as their production isn't as detrimental to the environment as monocell. Okay. And then your budget is another consideration. The average residential photovoltaic system, it costs between $16,000 and $21,000. That being said, there are a lot of tax incentives and leasing options that can greatly reduce initial expense. Many companies also have solar calculators that help consumers determine what size system works best to meet their needs. There are also the current tax credit in 2021 is 22% of the cost at 60 cents per watt rebate. Oh, no, I apologize. Yeah, okay, so for the tax credit is 22% of cost, and then Duke Energy offers a 60 cent per watt rebate for systems up to 10 kilowatts. I've heard that for the first half of 2021, they've already given out all the rebates that they're going to, but there might be some available for the second half of 2021. I think they limit the number of rebates that they give out every year. And then the final consideration is energy goals. The consumer's energy goals will affect the price of their system. Systems that are built to offset energy from the grid will cost less, but there will still be a monthly energy bill. Systems built to meet the complete energy needs of a home will be more costly, but energy savings will make up for those costs within a few years. The average residential photovoltaic system takes between 8 and 16 years to pay itself off. And then in regards to whether or not to install your own system, if you've got the know-how and the experience dealing with electrical and you've researched it, then I wouldn't discourage it. But the installation cost is roughly 10% of the cost of the system, and you can make up for that by getting multiple bids. If you shop around, you can easily get a 10% price difference between different companies, and in that case, it's good to have somebody installing your system who's done it many times before and knows what they're doing. So you can easily make up for that price difference just by shopping around. As far as maintenance goes, one great thing about photovoltaic is it really doesn't require much maintenance beyond cleaning. And you can just do that with water or, water and a squeegee. Just get up on your roof every so often and give them a little clean. The other thing that you do want to keep an eye out is power output. That combined with how old your system is gives you a good idea of when you might need to replace your system. It's usually when the output drops by about 20% and you're at your type of panel's end of life expectancy, then that's when you want to consider switching your panels out for new ones. Yeah, and like I just said, those are the two factors that determine whether or not you want to get new panels: is age and energy output. That's actually one of the disadvantages of photovoltaics is there's not a lot of resources for recycling photovoltaic panels, unfortunately. There are several recycling firms in the U.S. that are recommended by the Solar Energy Industries Association, including Cascade Eco Minerals. Currently, North Carolina regulates the disposal of panels based on whether those panels are considered hazardous or non-hazardous, and that just depends on what types of materials the panels are doped with to create the semiconductors. The North Carolina Department of Environmental Quality does operate a recycling markets directory website that can put citizens in touch with organizations able to recycle their panels. The recycled materials are either reused to produce new solar panels or they're repurposed and turned into other products. Unfortunately, the majority of panels in the United States are not recycled. So the advantages of photovoltaic power: it reduces your dependency on fossil fuels for your energy needs. It also reduces your energy costs, and it also gives you the chance to add energy back to the grid. They're totally silent. They have a pretty long lifespan depending on what kind of panels you get. They really don't have any maintenance beyond cleaning until you need to replace your panels. They can definitely increase your property value. That's just a given. And then the availability of silicone, it's the second most abundant element on the planet. So I predict we'll be making them for quite a long time. The disadvantages are acquiring the raw materials. You got to mine for the quartz sand, and that can have some damaging effects on the environment. And then the other disadvantage is disposal. You can see here, and like I said, most panels in the United States are not recycled; they're just thrown away. Some innovative photovoltaic technologies that I came across were photovoltaic paint. That one is not ready for the commercial market yet, but there are several types of photovoltaic paint being developed. So I predict one of those at least will become commercially viable, and that's basically just what it sounds like. It's a special type of paint. You put it on the surface and then hook it up electrically, and it can generate power for you just like a solar panel would. And then the other innovative solar technology is solar in part, I guess, is wireless energy transmission. The Japanese Space Agency has been working on this at least since 2016, and basically the concept is you send a satellite into space with a very large array of solar panels, and it will collect the sunlight's energy without having to deal with the atmosphere, and then beam that energy, convert that energy into a microwave, and then beam it down towards the earth where it can be collected. In 2016, the agency successfully transferred energy equivalent to 10 kilowatts using a microwave unit. The transmission distance is only 500 meters, which is nothing compared to the thickness of the atmosphere, which is more than 480 kilometers. But it does show progress. So I thought that was exciting if that's something they can turn into a viable energy source. And why I would use solar, I still would, despite some of the disadvantages and initial costs, just because you can use tax credits and incentives to help reduce those initial costs. You can also lease. It's silent, and it increases your property value, and it's better for the environment. And those are some of my sources. Thank you.
Oh, I had a question on this one here, Ben. So in the floating one is cooler. That is, it's so electricity actually is, or these actually work better at lower temperatures. So when we design these things, we design them for the coldest temperatures that's going to be around. That way we don't kill the system. We can, we can very easily damage a system if we overbuild it and don't think, don't take into consideration cold temperatures and stuff. So where are they putting these? I mean, are they just building waterways to put these in, or are they put them in existing waterways, or what?
These were water. For some reason, they had lakes that were somehow related to a coal operation. They were built for that purpose, and then the coal kind of dried up. So they've installed these there as a power source.
Nice. Okay, so it's basically a coal ash pit probably, and so cool. Very good.
Yeah. And I believe that was in the Anhui province where that's at. Yeah.
Yeah. So this is kind of an interesting map, and so when we're thinking about solar, in most cases we need the sun. And I'm going to take a shot at this. I don't really know exactly. but somewhere right in through here is our tropical lines. So we got the Tropic of Cancer, Tropic of Capricorn, and we got 100% sunlight in this area here. Looks like India, bottom of China, Mexico, maybe. But what's happening here? How come we don't have any here? How come we don't have any in this region? Any reason for that?
I'm sorry, I'm not quite able to tell what region it is you're pointing at.
Oh, so the New Hebrides, Philippine Islands, middle of Africa, and these regions. How come we don't have a lot of solar in these regions?
I imagine a lot of that's due to economics. I mean, there'd be a ton of factors. You'd have to clear a lot of that land is kind of in the tropical zone, so you'd have to clear forests to make space for panels, and then the GDP a lot of the countries in that area is pretty low.
Yeah.
So their governments can't afford to subsidize projects, and there's issues with corruption. So some of the countries just aren't very stable. So there are companies that are looking to develop solar outside of their home countries. It's probably not the ideal place to go, unfortunately.
Right. What is other than trees and stuff like that? What are other factors that hinder PV production?
As far as developing sites?
Why is it, well, for one reason, why is it not good in the East Coast where it is very good in the West Coast?
Oh, yeah, that's the annual amount of sunlight exposure. I had another map a little bit farther in that shows the average exposure. Oh, yeah, that first one there. So yeah, that gives you an idea. That's the irradiance average over the course of a year. And you've just got a lot more of it in the Southwest than you do over in the East.
Well, this gets the same amount of sunlight per day as this one does, as North Carolina, South Carolina. What's the hindrance for us that they don't have a problem with over here?
I'm guessing cloud cover.
Okay.
But
you are correct. It goes to moisture. Okay. So,
right.
And so right through here, we just said this is tropical rainforests. And, even if we, with the exception of right through here, the Sahara Desert, somewhere in that neighborhood, I don't even remember where it is, especially South America, the Philippine Islands and so forth, they have rain constantly, and, cloud cover, and just humidity in general. For us, in North Carolina, South Carolina here, we got, it's just humid all the daggum time. And so that, along with, soiling, pollution, stuff like that, you got to keep in mind that our cloud cover, our weather patterns run from west to east, and all of these people's pollution gets dumped on us. And so with all of that particulate in the air, then that kills our solar along with the moisture. One thing I want to correct here. So you were talking about, this is 100% the factors that we want. That is correct to a point. So back to this map, see, this is 35 degree, 40 degree So when we look at the latitude, that is what we want to be using as our best angle. And as this comes up, my son got into my computer over the weekend, and he says he's got a bigger processor in there. We'll see. I don't know. All right. So because of the Earth's curvature and where you are in relationship to that, then here in North Carolina, Western North Carolina, we're about 35.7 degrees. That's the latitude. So when we put up our solar, that is the angle to the Earth that we want to have. Okay, so if we get 35.7, that means that in the wintertime when the sun is down low and in the summertime when the sun is up high, we are somewhere right there in the middle. So basically, if you go to the spring equinox and the fall equinox, where that sun is there, that's going to be pretty much 35.7 for us. Now, when you get up here in Maine and so forth, then theirs are going to be even more, they're going to be more like this. When you get down here in Florida, theirs are going to be more flatter. So basically, when you're in the tropic zones, when you're down there below that tropic lines here, those can go pretty much flat. And so to kind of give you an idea, when I talk about these tropic zones, the sun goes back and forth. You know that we have, we have changes in the amount of time of light we have. Okay, so that's above these lines and below these lines. But here in the middle of this tropic here, this is going, the sun is going to be here in the wintertime. It's going to be down here in the summer, or vice versa. And so the sun just kind of teeter-totters like a ping pong ball between these two lines, but we still have 12 hours of sunlight and 12 hours of darkness in those two lines there. So those panels are going to be absolutely flat to absorb all that sun as much as they can. Now, if we're talking about, while I'm on the subject, if we were talking about solar thermal, where we're trying to get warm temperatures, then we might be more inclined to tilt our solar thermal panels to the winter sun, because we don't need to we don't use hot water in the summertime. We don't get in there and take super hot baths after we've worked outside all day long. So we'll tend to, probably about 15 degrees or so less in the wintertime, so that we can get them. But that's solar thermal. This would be PV, and we want to get maximum on that in PV. And something else we have to kind of play with is declination. So let's see, map of magnetic North Pole. So the magnetic pole moves all the time, and this gives you an idea of where that pole is at any given time. So from 1831 to 2020, the magnetic pole has moved, meaning that the solar south maintains the same, but we use a compass to find it, and we have to take into consideration of the declination of that. And this gives you an idea of the declination. So when we're trying to find solar south, and solar south is down here directly to the bottom, to the South Pole. But in order, if we were up here, then we're going to have to set our compass 20 degrees to the east. But where we're at, we're going to be about 7 degrees. And actually this changes all the time with that magnetic, with the magnetic movement of that pole. So you have to go to one of the NOAA sites and find out what the declination is of that particular day. Anybody got any questions for Ben? Ben, remind me again why we can't recycle these?
You can. The majority of the materials can be recycled and either put into new panels or repurposed into other products. The problem is that the know-how to do that safely. There aren't a lot of firms currently out there that are equipped to do that, and then there are also certain toxic chemicals, depending on the type of panel that you have. Some of them have heavy metals or things such as arsenic in them that you have to deal with safely. And yeah, there just isn't a lot of infrastructure in place to safely do that right now.
Good. We've always called this an ingot. And so the monocrystalline is, the best of the best of the best. And so we call this grown. Basically, like you were saying, it was, there's a lot of process that has to go through in this type. Whereas in the multi, so yeah, I meant to say this too. So polycrystalline is also known by another name called multi-crystalline. Since this being the mono or singular, then poly, also known as multi-crystalline, meaning many. And I've always considered this as a baking process. This comes out in a square versus the round ingot. And when you see these little triangles, these little diamonds in here, that is an indication of the monocrystalline cells, which are better, like you say, higher efficiency output and so forth. In the multi, you won't see those triangles. They'll be just perfect squares because, like I said, they come out like within a baking pan.
That's funny that you mentioned that. I actually saw a couple pictures of some really early monocrystalline panels, and they actually just left the cells as circles. Yeah. They didn't bother to square them up. I just thought that was kind of neat.
The 70s still. They didn't. They just left them as circles. Yep.
Yeah.
I want to add to since we're on this, I'm going to go ahead and add to this. Anybody else got any questions for Ben before I move on? All right, so we have a couple of different types of systems, and basically what we were talking about, that ingot is, he was saying that these cells sometimes were just perfectly round, and this is a cell. All right, and when we have a whole bunch of cells put together, we tend to call this a panel, but in the industry it's actually a module. We call this a module. When we take modules and group them together, we have what is called an array. And there's a couple of different things that that we have to consider when we make our arrays. One, what is the voltage? And secondly, what are the amp outputs? And these are of each one of these. So if we go in series, meaning the red wire is connected to the, sorry, let me try to draw this a little bit better. The red wire I'm just going to use different colors here. The red wire is connected to the, this needs to be blue, sorry. And this one needs to be red. So when we connect them like this, our voltage is doubled, but our amps stay the same. When we do them parallel, then our amps double and our voltage stays the same. So we have a little bit of play there in which we can work with that. Ben talked about some of these have their own inverter, and these are called micro inverters. And each one of these is going to have a micro inverter on it, and they put out AC, alternate current. And let me give you an example of alternate current. So when we have a Newton's cradle here, and what's going on there is we're moving an electron, and that electron hits another electron, which hits another electron, which hits another electron. And so when you're thinking about electricity, we energize an electron, that electron never sees the source. It just hits another electron along the way, and they kind of play this ping pong effect back and forth in alternating current. When we're talking about DC current, and AC current is what you have in your house, okay, 120 volt AC current. When we're talking about the car, we're talking about DC current, and that's kind of what this is. It goes in one direction. We're tapping this electron, and this, you know, and that in turn hits another electron, and so forth and so forth and so forth and so forth. So you have to kind of imagine that these are setting themselves back up again to do it all over again. And that is kind of a good analogy for direct current. Now, when we're thinking about our panels, and we have these micro inverters, and they all put out AC power, then by doing this, then we can hook right up to our house and we're ready to go. All right. We set this. Remember, I said that we add all of these up so that we either get 2 times the voltage or 2 times the amps. And then we set it into motion that goes into the house. Now, with this type of system, we can't just plug into the power grid. And the power grid is all of our poles, you know, all across America, and all these lines going across through here. That's what we call the grid. We can't plug into this because this changes. The amps and the voltage are constantly changing due to sunlight, due to conditions. Like today, for instance, there's no way in the world that we can get 100% voltage out of our panels because there's a lack of sun. All right, so the grid, it has to have, you are guaranteed equal to or greater than 110 volts, but equal to or less than 120 volts. So what happens is over here at the power company, they have they're making power, and it is 100% 120 volts. But by the time it gets up to your house, it may only be 110, but the power company guarantees 110. So it can fluctuate between 110 and 120. Unfortunately, these fluctuate from 0 to whatever they're rated at, and each one of them might be rated differently. So when we're thinking about the grid, and like I say now, the microinverter is a fairly new thing. Generally, they're DC. All right, so they're like your car. You can go and plug your car up to them and crank up your battery. Hang on just 1 minute.
Are the ones that they built here a year or so ago, are those DC or AC where they got the station set up where you can plug your computers in and phones and all that?
Those are DC, but they have an inverter.
On each panel?
No, they have the inverter is inside under the table.
Oh, okay.
Yeah, that was my program that set these up, that set those up. So you get a DC, so you can connect all of these together, and there's a couple of things, couple of different systems that you can do. You can do a direct, and that is that's saying that you're going to catch sun, and you know you're going to be over in Texas somewhere where you're trying to get water from a deep well. So this may run to a pump that's down here, and we have a big tank above ground, and when we have sun, this thing runs and it pumps water up into the tank. That's direct. Or it may run a fan, or it may run well, okay, so I was talking about solar thermal a minute ago. So we've got a solar thermal system up here, and we have our storage tank below. So we want hot water to come down here. We know that hot water is pushed upward by cold water. So the hot water is going to stay up here if we don't put a pump on it. So if we put a pump on it and we have a PV panel on there, when the sun hits this and has enough energy to make it hot, then it's going to turn this pump on, and it's going to travel. It's going to have water pumped up through here so that it makes it hot and puts it back down here. The second way is battery bank. So in a battery bank, we have a whole bunch of batteries set up, and these are wired to them in much the same way that I explained to you a minute ago. So we can put these in series. And have a certain amount of voltage. And we have what is known as an inverter. And the inverter changes it from DC to AC. All right, so these batteries are all DC. So we have to have an inverter to change it over into AC so that we can use it in our house, because our house is mostly AC. So, you know, we work until these are dry, and then we work off of the grid. Or if we're, you know, if we're not on the grid, then we're just SOL. So we can do what the last system is, a grid tied system. And this seems to be the most popular. So in this system, we don't have any batteries at all. We could, but we normally don't. And these are all tied into this inverter. So we got DC going in, we got AC going out, and it goes directly to the grid. But this is what is known as a grid smart inverter. Meaning that if for some reason a tree falls on this line over here and breaks the line, then there's not going to be, this thing is not going to sense a phase in here, and it's going to shut down. It's not going to allow power to transfer up, because when Fred comes out here with his truck and has to work on this, and he touches that line that is not supposed to have anything on it, it's going to kill him. So out here on this pole right at our house, we have what is called a transformer. So the power on this line here is about 13,000 volts. But we've already talked that down here at our house, we have 110 to 120 volts. So this steps it down to the 120, 110, 120. However, if it's going in the opposite direction, it steps it back up to 13,000. So old Fred here, he's going to put these two lines together, and it's going to knock the piss out of him, and it's going to kill him. So that's why we have a grid smart inverter. And this is supposed to be anytime that you have a generator or anything tied to your house by law, and this is highly enforced. If you grab a generator and you just go, you know, hook it up to your panel to run your refrigerator or whatever, and old Fred gets killed, you are looking at involuntary manslaughter charge. So anytime that you anytime you hook up, so if you were to do something redneck like that, and that's very redneck, you go into your main and you make sure it's off. Both of them, all of them. Make sure they're in the off position. That way it does not go out, because you don't want that kind of business going on there.
What do you call the generators that are wired in where if the power's off?
They have a grid smart breaker on them.
So it kicks in after the power's been off for maybe 60 seconds to run the house, correct?
Well, it kind of works in a check valve, if you're familiar with that. So let's put it into, let's build us a pipe here. And in the middle of this thing, we're going to put us a check valve. All right. So water generally flows in this direction and it opens up a little check valve. All right. So this thing swings. And if water were to ever try to go in the opposite direction, then of course this is going to slam shut and it can't go in that direction. It's going to stop it.
Like our heart valves.
Sure. Yeah. Well, there is an electrical thing. I don't know what it's called. It's a check valve. Works the same way. Electricity will only flow in one direction. So when you fire that generator up, and you know, if you have a generator in your house, you better fire that thing up on a monthly basis and let it run for 30 minutes. Or, you know, like right out in Texas, after they got all that big snowstorm, nobody's generator worked because nobody ever cranked it. The worst thing for an engine is to let it set and not run. Last call for questions.